Welcome back, everyone, and this is Professor Bright. Today we are going to learn about inverse functions, and you can see there's going to be 5 videos in this video series, and really all we want to be able to do by the end is find the inverse function and, if it exists, state its properties. So there's a few things that we need to talk about: injective, and then there's some properties, cancellation laws we call them, and then some nice graphical and algebraic properties that go along with the inverse. So but before we get there, I want to let you know we are going to be coming up on exponential functions and logarithms, so prepare as needed. But also, we want to return to an example that we saw that actually may have some bearing here. So you might remember back when we were looking at linear functions, we were looking at this example with Celsius and Fahrenheit and converting between the two temperature scale systems. And so we gave this bit of information. So 0 degrees Celsius was the same as 32 Fahrenheit, and 100 Celsius is the same as 212 Fahrenheit. So we wanted to be able to construct a linear function between them. So that is to say, in this particular language, it says Celsius as a function of degrees Fahrenheit. So that means we're going to write a function where formally we would write this as like C of f. So independent variable is f, dependent variable is c. And so if we were to do something like that, so we're treating f as like our x coordinate. So we'd have 32, 0, and we'd have 212, 100, and if it is a linear function, right, we can find a slope. Okay, so 100 minus 0 over 212 minus 32, and we end up getting down the road 5/9. Okay, if you fully simplify it. And then slope or point slope form, so then we have c minus 0 is equal to 5/9 of f minus 32, and really this is enough for us. You could distribute if you wanted, but formally I'm just going to kind of wrap this up and say c of f is equal to 5/9 of f minus 32. Okay, and that's how you can convert between or from Fahrenheit to Celsius. Okay, and so then in the video there was this question about domain and range, which went unanswered. A couple of you asked in class, and so we clarified that. But for the domain and range of this, not completely clear based on the context. You might say, oh, it's a linear function. It has domain all real numbers. Well, we're in a context, right? The lowest known temperature is absolute 0. And in Celsius, which corresponds to our range, in Celsius, absolute 0 is negative 273.15 degrees Celsius, and then the temperature can really go to infinity, so it can get as hot as we want, but we do have a lower boundary. For the domain, might want to confirm this, but last I recall, absolute 0 in degrees Fahrenheit is negative 459.67, and then off to infinity would be the domain here. Okay. So we have this domain as the range of Fahrenheit, and then the temperatures which we can have in degrees Fahrenheit, and then the range here is the values for temperature that we can have in degrees Celsius. Okay. Now, in this example, we also said, well, what if you went the other way? What if you wanted to express Fahrenheit using degrees Celsius? So now we're kind of switching the order on us, and we're looking for f of c. So, okay, well, we can certainly use what we have here. I'm just going to write this, get rid of the function notation, and just say this is c is 5/9 of f minus 32. Okay, and then resolve, so multiply by the reciprocal, so I'd have 9/5 of c, and then add 32, and boom, we have Fahrenheit. Okay, so then formally we would say that Fahrenheit is a function of Celsius degrees, and this is going to be 9/5 c plus 32. Okay, and then if we want to look at the domain and range, again, it's not going to change really from what we had in part B. It's just going to kind of flip. So the domain here is this idea of negative 273.15 to infinity, and range now is the values that we can have for Fahrenheit, so negative 459.67 off to infinity. Okay, and so kind of something interesting to point out is that what was the domain for one function ended up being the range for the second function, and vice versa. The range became the domain. That's kind of interesting. Now, what I want you to do is plot these on Desmos. Plot the two functions. You can use x and y. So really, what we're going to be graphing is like y is equal to 5/9 of x minus 32. And just for ease of graphing here, we'll also graph y is equal to 9/5 of x plus 32. Okay, so let's get that set up. And so here, I paused the video and graphed these things, so they're both shown here, and so I'm just kind of curious what you notice. So pause for a second here and see if you can identify anything interesting on this graph. Okay, well, I kind of noticed, well, they meet at minus 40. We saw that before, but they kind of look to me like they are sort of almost, well, I mean, they have different intercepts, all that stuff, but they look almost symmetric, right? Like they meet here, and then if you kind of imagine like a dotted line that goes like right between the middle of them, right? That could be like the line of symmetry almost. And so that's kind of interesting. Maybe that's valid. I don't know. Probably is if I'm saying it, but you know. Just have to point it out there. Okay, the reason we're bringing these functions up is that these are actually inverse functions because of the way we solved them, and you'll see that later on. So when you're solving for one variable and then switching it and that sort of thing, that's the idea of inverse functions. And that symmetry that I mentioned, that does pop up a little bit too. But yeah, these are actually inverse functions. So we'll see more properties related to inverse functions in the next video.